Okay, so we are doing the conservation of momentum notes. The date would be either the 22nd or 23rd, depending on which day you guys have class. So, this is the idea that we are talking about momentum is conserved before and after collisions. So, we're going to talk about both of the different collisions that we have as well, including some math that goes along with those collisions. But the whole premise is that you have to remember momentum is equal before the collision and after the collision because it is conserved. Okay, so we all have to remember that. I'm going to put it down. Let's spell it correctly. Momentum is conserved. And I'm going to put in parentheses the same before and after a collision. Okay, so that's the conservation of momentum that we have to remember while we're doing these problems. Okay, so the first type of collision we'll do is an elastic. We've talked about it a bunch of times, so we should remember what it is just by our discussions and our interactive we did. So an elastic collision is the objects bounce away from each other or apart. I'm going to say apart just because when people think away, they always think opposite directions. They don't always go opposite directions. Sometimes they move in the same direction after. So they bounce apart, meaning they just don't stick together from each other. And kinetic energy is conserved. So remember, kinetic energy is the energy of motion. And to have motion, you have to have velocity. So when we get into energy, which is our next unit, we are going to talk about how to solve for it, which will be involving the variables, both mass and velocity. So if kinetic energy is conserved, that also means you're not losing velocity in the equation. So again, perfectly elastic collisions in the world don't exist except for on the molecular level and within electrons and the movement of particles at that level. We do not have perfectly elastic collisions in the real world because we have things like gravity and friction and air resistance. So those things do not allow a perfectly elastic collision unless you've closed the system in a situation where there's no friction, no gravity, no air resistance for you to have. So we have to remember that. So even though kinetic energy is conserved in a perfectly elastic collision, in the real world, we'll have mostly or partially elastic collisions, and you will lose a little bit of that velocity through the kinetic energy that is lost. Okay? And that's when we hear sound. So you're going to hear sound in a collision. Even if you feel like most of the velocity was conserved, a little bit of that energy was lost in the form of heat or sound. Okay? So in this case, though, we're going to talk about perfectly elastic collisions. And even if you lose some velocity in a collision, you're not going to lose momentum. That is always conserved no matter what. Okay. All right. So to do the equation, we have to remember that momentum initial, that's the momentum before the collision, is always going to equal the momentum after the collision or the final momentum. So remember, P is for momentum, I initial always equals momentum after the collision. Now we also know to get momentum, we have to have mass times velocity. So we're going to have the mass of object A. So we'll just say object A. It could be object 1, it could be object A, object whatever letter it's assigned or number it's assigned. But we're going to just use A now as being the first object. So we're going to have to multiply, mass times the velocity of A. So in the case of our collisions carts, our red cart could have been mass A and velocity A. And we're going to add that to the other object. So we'll just call that object B. So mass of object B times velocity of object B. So that will be the entire before the collision. You have to have whatever the first object is, its mass and velocity, and whatever the second object is, its mass and velocity. We're going to multiply those together first and then add them together. So you multiply mass times velocity, get momentum of each object separately. Then you're going to add those two objects together. Now that has to equal the momentum after the collision. Since the objects bounce apart from each other, that means they're going to stay separate after the collision. So now you're still going to have a mass of object A, which should not have changed. So that'll be the same number, but you might have a different velocity. Now, the little hash mark here means after velocity. So when we're talking about after the velocity, we just put this little hash mark after the collision, we put this little hash mark by the velocity because that means we're talking about its velocity after, which is different than its velocity over here, which was at the beginning. So the hash mark means after. Plus, we got to do the same thing with object B. Mass of object B times its velocity after the collision of object B. So it looks like a lot of variables, but really just think about what it is. You're taking each object's momentum before the collision, adding them together, and their object's momentum after the collision, adding them together. Those numbers have to equal each other because that's the principle of the conservation of momentum. So we're saying they will equal each other. So what's going to happen is we're going to be missing maybe one of these variables, and we're going to have to find it knowing that these two sides have to equal each other. And that's why this math works out very nicely. So to start it out, I'm going to actually separate a before and after. So as you get better at these, you won't have to do all these steps. But to start it, I'd like to do all these steps because I want you to get used to how to do this. So before the collision and after the collision, I'm kind of making a T-chart here so I can get any information that I have laid out here. So I could give you a story problem and you would have to put down a picture or write down the variables that are from the story problem, or I can just give you a visual, which in this case, I'm going to give you a visual, okay? We're going to have two balls, A and B. A is going to be traveling to the right towards B, which is stationary. So these little quotes around it is saying that the ball is stationary. There's no velocity, okay? And I don't like my A. I'm going to redo that. Keep breaking my lead, just like you guys know. Every single time I start, oh, there we go, broke it again. Every time I start these, I break up my lead. Okay, so now we have the two balls. A is going towards B. So each one needs a mass and a velocity in order for us to find the momentum. So we're going to say the mass of object A is going to be 2 kilograms. We'll do this like we did in our first interactive on the collisions interactive we did last week. We're also going to say that it has a velocity of 5 meters per second. So we're good there. We're going to give the second ball, we're going to give it the same mass because let's just say maybe it's like a billiards ball, playing pool. They're the same mass. They're going to collide. But this one, since it's stationary, has a velocity of 0. So we now know that we can figure out the momentum for each of these separately and add them together to get the momentum before the collision. We want the total momentum. So we're going to do mass times velocity, just like this, mass times velocity of object A. So we're going to do 2 kilograms times 5 meters per second. And we know that 2 times 5 is going to be 10 kilograms meters per second. That is the momentum for the first object A. Now we're going to take the plus sign. We're going to add it to the momentum over here. Well, this one's a little easier to do in your head because we know that 2 times 0 is going to be 0. So the object B does not have a momentum. It's stationary. Remember, you have to have velocity to have a momentum. So now we're going to add these together, and it's just going to tell us that the momentum before the collision for both objects is 10 kilograms meters per second, because one object's moving, the other is not. Now we know that that has to equal what happens on the other side. All right. So after the collision, what's going to happen is A is going to come to rest. So A will collide with B and it's going to come to a rest. Now B is going to take off to the right. Now what did not change was their mass. So we can't, even though I look like I drew it bigger, we can't change the mass because that doesn't happen. But we do know the velocity changed. So in this case, we know since this one came to rest, its velocity is going to be 0. Well, here's our question. What is the velocity of B? That's what we're going to look for. So we have to start with the second half of this equation up here. So now we need mass times velocity plus mass times velocity of objects A and B. So mass times velocity, 2 kilograms times 0. And we're going to add that to what's happening over here. So 2 kilograms times 0 is 0. So there's no momentum of A, kind of like the beginning of the first one of B. But we don't know what the momentum is here yet. We're going to figure that out because we know that it's going to be 10. Okay, but we have an X here. So the question is, because we don't know the velocity here, we know that it's going to equal 10 kilograms meters per second, but we want to find the velocity. So since 0 plus this is just 2 kilograms times x meters per second, I'm going to drop that down there because the 0 doesn't really mean anything when we're adding it together. Now, if there was a number there, we would have to deal with that number, and we'll do that in a future practice. So now I want to get x by itself. I need to get x by itself because I want to know the velocity of ball B after the collision. And because I know that these have to equal each other, I'm just going to get rid of the 2 kilograms. Since they're being multiplied, I'm going to divide out 2 because 2 is being multiplied by x. To get rid of it, I do the opposite of multiplication, which is division. And when I do to one side, I have to do it to the other. Now what cancels is kilograms. 10 divided by 2, and I'm going to be left with meters per second because that's what I'm looking for is a meters per second, x, right? So 10 divided by 2, I already know that is going to be 5 meters per second. So the velocity of ball B after the collision was 5 meters per second. Well, if it started at 5 meters per second in a closed system, no friction, once it collided, we knew that that transferred 100% of its momentum over to ball B, and ball B is now going 5 meters per second. So that is how you solve an elastic collision using the concept of conservation of momentum. So let's do an inelastic. Now those obviously are easy ones to start with, so we're going to get a little harder as we go on, but we'll start with the simple ones. Inelastic collision. So we know that inelastic, the objects stick together. After the collision. Stick together after, I need the word after there. And they move, I'm just going to put this out so we can remember, and they move as one mass. So that will remind you that they become one mass after the collision. So in this one, KE, which is kinetic energy, like I said up at the top up here. So kinetic energy was conserved up at the elastic. In a inelastic collision, kinetic energy is not conserved. I'm going to squeeze it in over here. Is not conserved. So in an inelastic collision, when there is some sort of stick together, a lot of times you see this in a car accident. There's damage to the car. There's crumpling of the car. They may stick together and even move together after the collision, depending on how big the mass of the the cars are in the collision and how fast they were moving. But the damage and the fact that they stick together, you lose kinetic energy because it's lost inside the actual system of the car crash. So the cars absorb it, a lot of that energy. You'll also still hear the sound and have the heat, but there's definitely, even in a closed system, when there is kinetic energy not conserved, when there's a collision that's inelastic, okay, a stick together collision. So you have to remember that. All right, so to do this one, the same principle of, initial momentum equals final momentum. Same thing. Conservation of momentum still applies here. So the difference is what happens after, and that's the only difference in our math. So we're still going to have the first part of the equation the same. So the mass of object A times the velocity of object A is going to be added to the mass, there we go, the mass of object B times the velocity of object B. Before the collision stays the same. After the collision, they stick together as one mass. That means after the collision, you have the mass of object A plus B times the velocity, because they're together, you're only going to have an after velocity. So we consider it one velocity because we add together the mass of object A and B. So it's a pretty simple concept after you think about it. Don't worry about all this variable stuff. Just remember, add the masses together after and find the one velocity. Okay, so let's try that. Let's go with a before and after, just like we did before. So I'm going to split it down the middle. Now you don't have to do all these steps once you get used to how to do it. You can just write out the information and solve. But sometimes, like I said, if I give you a visual and I tell you a mass and a velocity of the first objects, you may want to write it out just to help you keep all the information together. Okay, let me get it so I'm at the end of my paper, y'all can see it. Okay, before, so let's say we have a train car A. So train car A is moving and it wants to attach to a stationary train car B. So again, like I said, we're starting pretty simple. So train car A is moving to the right, train car B is going to stick to it. It is stationary. Train car A is going to have a mass of 1,200 kilograms. Train car B is going to have a mass of 1,800 kilograms. So B is definitely larger than A, but A is going to have a velocity. It's moving while B does not have a velocity. So let's say the velocity of A is going to be 30 meters per second. Velocity of B is 0 because it's stationary. Remember those parentheses, quotes, those mean that you have a stationary object. So same thing applies in the beginning, mass times velocity plus mass times velocity. So we know that the mass is 1,200 kilograms times the velocity of A is 30 meters per second. Over here, mass 1,800 kilograms times 0. So we know that that's going to end up as 0. So we're going to just do that right now, 0. Well, 1,200 times 30, that's something you're actually going to want to plug into your calculator to make sure you got it right. You could also do 12 times 3 and add the zeros, but I always like to show you to make sure you know you got it correct. So 12 times 3 is 36, and you add all the zeros, you get 36,000. So 36,000 kilograms meters per second plus 0 ultimately equals, and I'm just going to move it down here, 36,000 kilograms meters per second before the collision. I'm going to erase this line so I can merge my equation down here. So that's the momentum before the collision. Because only one cart had momentum, we figured it out. And we are knowing that after the collision, the momentum will stay the same. So it's going to be 36,000 kilograms meters per second over here, but we're going to have a missing variable defined. So after the collision, A is now hooked up and stuck together with B. So the train cars are now moving together to the right, okay? Their masses didn't change. So remember, mass equals 1,200 kilograms. But according to this, we have to add them together because now they're one. So plus 1,800 kilograms equals 3,000 kilograms. So the mass is now added together at 3,000 kilograms. The velocity is what we're going to be looking for. We want to know what's the velocity of the two carts together as they move after the collision. So set up a simple mass times velocity. So 3,000 kilograms times x meters per second. There's nothing we can do over here. Because this is one object at the end, we don't have an additional object we have to deal with. So we're just going to move that down to the bottom. I'm running out of space to write with my hand hanging off the table, so my handwriting's gotten a little gross. So now we need x by itself. So we do what we did on the top one. We got to get rid of the 3,000 kilograms by dividing it out since it's being multiplied. So divide out 3,000 kilograms, so it cancels. That leaves x by itself. Got to do it over here. Ooh, my handwriting's so bad when I can't rest my hand on the table. So 36,000. So again, if you just can do that by your head or in your head, you could divide out 36 by 3, which most of us know is 12. Oh gosh, I'm running out of space down here. So 36,000 divided by 3,000 is going to give us 12. So, you can cancel out all those zeros and just know that that's 12. I'm going to squeeze it in right here. I'm going to say after the collision, and remember kilograms cancel, they're going 12 meters per second. Ooh, fit it in there. So 12 meters per second is after the collision. So you can see the velocity decreased by a lot because it was originally 30 meters per second. If it would have bounced off of it or pushed it, then they would have transferred the momentum. Velocity would have stayed the same, right? 30 meters per second. But because they stuck together, they lost that kinetic energy, which means their velocity went down, and therefore now they're only at 12 meters per second after the collision. Okay, so there are two examples of pretty simple problems. So I'm going to flip it over and we're going to try to do a little more complex problem where maybe the objects are both moving instead of being stationary. Got to make sure we have the right. There we go. And I was on page, I think 21. 21, so now I'm on 22. Ah! And it's still the same days. 222 or 223, depending on your class period. Okay, so now let's try a more complex one. I'm going to give you a story problem where you actually have to figure out what's happening. So we'll start again, and I'll just give you the hint that this first one's going to be an elastic collision. So you don't have to decipher that, even though you should be able to know based on the fact that it'll talk about whether it's stuck together or pulled, bounced apart. So ball A is 15 kilograms and is rolling at 7 meters per second. 7 meters per second, that's a 7, toward ball B, which is 10 kilograms and moving, oops, it's an I, moving 2 meters per second. Now pay attention to positives and negatives. That's going to tell us the direction, and that's key. So don't automatically assume that they're coming at each other. Pay attention to the negatives. Negative is left, positive is right. Okay. After the collision, Ball A comes to a stop and, oops, not and, let's say what is the velocity of ball B? Okay, that's a lot of information it feels like, but just the best way to start this is figure out what you have for each of the objects before the collision, and then we'll do the after on the next step. So before the collision, we have two balls, okay? Ball A is rolling at 7 meters per second toward ball B, so there's a second ball, which is moving 2 meters per second, but notice it's still a positive. So ball A was going to the right because it was positive 7, and ball B is also moving to the right as well. So I'm always going to put the directions of arrows up above my diagram. So when I do ask you to do some of these problems, I'll ask you to diagram it with the arrows of direction, okay? That shows me you understand the actual motion of the ball. So both of them are positive. So let's talk about the mass. So I'm going to underline before the collision all the things we have. We have a 15 kilogram ball, which is ball A. So the mass of ball A is 15 kilograms. The velocity, remember it's positive, 7 meters per second. Now let's look at ball B. 10 kilograms is the mass. Its velocity is 2 meters per second. So again, positive means to the right. So both balls are moving to the right. So this guy's going slower. This guy's going a lot faster. So it's eventually going to catch up to it and knock it. All right. After the collision, let's line up kind of what happens just so we have it. We'll solve in just a second. So after the collision, ball A comes to a stop. That's really important. So ball A now has stopped. Did its mass change? Absolutely not. 15 kilograms. Since it's an elastic collision, their masses stayed separate. It comes to a stop, so that means we know its velocity is also 0. Ball B, okay, has a mass that didn't change, so it's still 10 kilograms. But we do not know the velocity. That is what we're going to look for, is x, meters per second. Now, some of you could probably look at the problem and realize, wait, if they're both moving to the right, we obviously know that B is going to continue moving to the right. There's no way that after A knocks it, it's going to turn around and come back the other way. So we know it's going to be a positive number when we solve. We also can see there's no negatives anywhere in either side. So therefore, when it comes out at the end, it should be positive. Okay. So that tells us automatically it's going to go to the right. So you can draw that up there in the beginning, or you can wait till the end and know, okay, it's positive, it's going to go to the right. All right. So now we need to solve before and after. So let's start with before. We know it's mass times velocity plus mass times velocity. So it's going to be 5 kilograms times 7 meters per second plus 10 kilograms times 2 meters per second. So this is going to give us the momentum of them separately, and then we're going to add it together. Because remember, you always have to multiply first before you add. So 15 times 7. I don't know why I wrote 5 right here. It's like, wait a minute, I swear it was more than that. So 15 kilograms. 15 times 7, you can just pop it into your calculator, and you're going to get 105 kilograms meters per second. So the second one is 10 times 2. So we're going to add that still, bring down our plus sign. 10 times 2 is 20 kilograms meters per second. So our individual momentums are figured out, 105 and 20. Okay. Now we have to add those together because we want the total momentum before the collision. So 105 plus 20, you can probably do that in your head and say it's 125 kilograms meters per second before the collision. So remember, we know that everything before the collision has to equal everything after the collision because momentum is conserved. So we know this momentum over here is going to end up being 125 kilograms meters per second. That's what allows us to find x. So now let's do the second side. Mass times velocity of object 2, 15 kilograms times 0, plus 10 kilograms times x meters per second. So it's a little bit different than last time, okay? So now we have these two numbers, but good thing here is you don't really have to worry about what this is. 15 times 0 is going to be 0 plus 10 kilograms times x meters per second. And since I add those together, 0, you just get to really bring this down. So 125 equals 10 kilograms times x meters per second. I got to get x by itself, so I got to get rid of the 10. Means I divide out 10 kilograms on both sides. Kilograms get canceled, and that leaves us with 125 divided by 10 is going to be 12.5 meters per second, because that's what I'm left with. Okay, so that was only slightly harder because we took away the 0 on this side. So we had to actually add together our momentums. And we didn't take away the 0 over here, but we will do some problems where you actually have to do something with that number. All right, so let's try another inelastic. So inelastic in this case, I'm going to slide up the camera. So we know these are going to stick together and become one mass after the collision, but let's give you a story problem to figure out. So a 16, oh, maybe this is not an inelastic collision. Let's see. I want to make sure I give you an actual inelastic collision. Sorry. Give me a sec as I go through my notebook to find an actual inelastic collision for you to practice with. Well, you know what? I have the wrong notebook, so I'll just make one up. So let's say a train car, I always use train cars for them because they stick together, but we could have done anything, a magnetic cart or whatever. A train car is, A, we'll say A. A is 800 kilograms and moving at 15 meters per second toward train car B. Okay. B has a mass of 1,300 kilograms and a velocity of 4 meters per second. Okay, -4. We want it to be moving towards each other. So it's a -4 meters per second. That's the hint and direction there. What is the velocity of the carts, or the cars, and I could have said train cars, but you get the gist, after the collision? That's what happens when I make them up in my head. I say weird things that don't make sense. So that was on the fly. So let's go ahead and figure it out, though. The good thing is you can figure it out no matter what because the conservation of momentum exists. So the bad thing is I have no idea what the answers are right now because I haven't done this one yet. So a train car is 800 kilograms, train car A, moving at 15 meters per second. So remember, we want the before. We're going to have train car A. It's got a mass of 800 kilograms and a velocity of 15 meters per second. And then it's going to collide, because it's moving to the right, with train car B. This would probably never happen in a real life situation where they'd be coming at each other like this, but that's okay. A mass for train car B is 1,300 kilograms. And its velocity is a 4 meters per second. So it's going the opposite direction to the left. They're coming at each other. So that negative is important for us to remember to keep in our problem. That really helps us understand the direction after and also what the velocity is going to be correctly. So let's do the after and just get it written down so we have it. Remember, it's going to become a sticky collision, so they're going to stick together after and become one mass. So they're moving together. And I'm not going to put a direction yet. Let's solve it first. Now, some of you could look at it and probably take a good guess at direction after based on momentum. But right now, we'll wait till we solve, and then we'll put the arrows after. So remember, mass times velocity plus mass times velocity is always before. It doesn't matter what kind of collision. So we're going to have 800 kilograms times 15 meters per second. That's the momentum of train car A. Goodness. Plus, we're going to do the momentum of train car B. And it's a -4. I got to remember to do that. See, I just have to remember my own advice. Don't forget the negative. Now, I'm going to plug that into my calculator. And I'm going to do mass times velocity first. So it's going to be 800 times 15 is 12. There we go. Is 12,000. So we're going to have 12,000 kilograms meters per second. Plus, now we do 1,300 times -4. So 1,300 times 4 negative is -325 kilogram. Wait a minute. I must have done something. Hold on. Yeah, I was like, there's no way it's 325. Huh. I hadn't cleared something out. I was like, 1,300 times 4 cannot be 325. So let's try that again. I'll show it up to you on the calculator. See, pay attention when you're writing things down, because sometimes your calculator shows you something because you hit your button wrong. And then you hit it wrong and you end up with the wrong answer. So use your brain a little bit too when you're using your calculator. I plugged it in wrong because I was like 325 makes 0 sense there. So 1,300 kilograms times 4 negative is 5,200. So -5,200 kilograms meters per second. So paying attention to what you do is super important. So now I need to add these together. So I'm going to clear it out just so we can see the whole process, that I don't make a mistake. So 12,000 plus 5,200, and I always have to add the negative after on my calculator. 5,200 equals 6,800 kilograms meters per second. And it's positive because the negative number here was much less than the positive number. So kilograms meters per second. So that's the total momentum before the collision. Now I need to remember that's going to equal what's over here. So therefore we can solve for V because we know they're equal. Now after the collision, they stick together, the masses become one. So we have to add them together. So 800 kilograms for cart 8 plus 1,300 kilograms for cart B or car B. So we add them together. So 1,300 plus 800 is going to be, oh, that's not right, 2,200 it should be. Or 2,100, sorry, 2,100. Yep, kilograms. There we go. See, checking my own brain again. Now I need to look for velocity. So I know the mass, the velocity is going to be x meters per second. We want to know the velocity after. So mass times velocity is our momentum. So 2,100 kilograms times x meters per second. And since there's nothing else I can do over here, I'm just going to drop it down so I can solve with my other side of the equation over here. So I'm looking for x, the velocity. I need to get rid of the 2,100. By getting rid of it, I have to divide it out since it's being multiplied. That means I have to divide it out of this side as well. Cancel out my kilograms. And now I'm going to plug it into my calculator. 6,800 divided by 2,100 is going to give me a decimal because I made this up in my head, but that's okay. After the collision together, they're going to move 3.2, and let's just go one more digit out for the sake of space. So 3.24, because I rounded up, meters per second after the collision. So you lost kinetic energy. That's why it slowed down after the collision. It's slower than both of their original velocities of 4 and 15. Okay, and it's positive. That means after the collision, we can draw our arrow now. The objects move to the right. Okay, so there are a lot harder ones that we'll eventually get to, but we'll save those to practice. And when I say harder, not much harder. Like both objects might have a velocity after the collision on an elastic, where you're going to have to deal with, instead of this being 0, you're going to actually have to deal with it being a number. We'll practice that together in class, and there will also be some entry tasks for that. Okay, so that is it for now. And I'm going to stop it.